Hello, ladies and gentlemen. My name is Reagan,
I'm Carl Spivey.
And I'm Anthony Presot.
and we are cadets at the United States Military Academy. We are group number 1083, and we chose to model Problem B, the bike throw. Our coach is Major Caleb Sheffield. Problem B regards the situation of Ruth Winder, who won the Brabantse-Peel-Dam cycling race on the 24th of April, 2021. We wanted to know how she could have won the race while being behind the biker next to her immediately before and immediately after crossing the line. Our model determines when the bike throw would be most effective. Our approach to starting to model the situation was to begin with a brainstorm. First, we tried to figure out what was actually happening. We did this by drawing free body diagrams, talking about physical concepts, and comparing what would happen as we increased or decreased different parameters. Then we created a really rough model with some general parameters. We continued to refine our model by adjusting sliders and getting rid of the factors that we could not successfully incorporate, and those ended up to be our limitations. Then we used our model to evaluate the distance Ruth Winder gained as a result of her bike throw, and further we drew conclusions about the conditions required for a bike throw to be beneficial no matter who was riding it. In our model, the independent variable was time in seconds, and the dependent variable was the gain in distance in meters. Here are the parameters that we considered would affect our model. First, we had mechanical friction, which is contained within the mechanism of the bike. Then we had air resistance, which would slow the bike down. Next, we had the mass of the bike and the biker. Then, the speed at which the biker was moving before executing the bike throw. Additionally, we considered arm length because it would affect how far the bike could move forward during the throw. After that, we talked about how area as a function of height would be important because the air resistance would act on the frontal area of the rider throughout the throw. And lastly, power would determine the speed and force of which the biker could push the bike in front of themselves. Then we've substituted in the values specific to Winder's situation. We obtained these values in 3 different ways. 1, researched, 2, calculated, and you will see the relationships that we use to calculate these actual numbers later on in the presentation, and 3, assumptions, which you will also see.
Assumptions made in our model is that the rider is in optimal gear and does not change gears before, during, or after the bike throw. Additionally, the rider has positive control of the bike throughout the throw. We are assuming that wind, road condition, and friction are all constants in our model. The biker is wearing minimal resistance clothing and skin or friction is negligible. Additional assumptions include that the road is flat, that the front wheel of the bike makes up 5/12 of the surface area of the front of the bike, that the power of a bench press for a man is proportional to the power of the bench press of a woman, that the bike is an Olympic grade bike and hence would have a mechanical friction of 0.5%, that the rider has standard arm proportions and standard height to mass proportions. We're also assuming STP conditions, and for Ruth Winder specifically, we are classifying her as an elite female athlete having a power of 1600 watts.
Our model for the position of Winder during the bike throw was a second order nonlinear differential equation with the initial conditions at time of 0, a distance of 0, and velocity equal to the velocity of the biker who does not throw their bike. In the model, M is equal to the mass of the rider in kilograms, M_B is the mass of the bike, K is the coefficient of air resistance in kilograms per meter, X is the distance in meters, and T is time in seconds. Since we could not make measurements on Winder herself, we found, using research, proportions, using her height and her mass, and we have an equation for arm length and frontal area, and the velocity of the other biker was found using the force of air resistance and the force of the biker using the power that we found for elite female athletes, and using that we have the velocity is equal to the cube root of the power divided by the coefficient of friction. Using the equation for air resistance, we found that the force of air resistance is 1/2 times the drag coefficient of the rider times the frontal area of the rider times the density of air multiplied by the velocity squared. And using the velocity of the other rider that doesn't throw their bike, we have an equation for the distance that the other biker travels. So our model, which is represented by D0, subtracted from D1, will show us the distance between the two bikers after the bike throw. After solving our model for the distance that Ruth Winder travels and subtracting the distance of the other biker, we can see that the maximum distance Ruth Winder and her bike will be ahead of the other biker is approximately 0.6 meters, and approximately 1.1 seconds the other biker will pass Ruth Winder because she will stop pedaling and air resistance will take over. So after Ruth Winder initiates the bike throw, her bike is not instantaneously that distance ahead of the other biker. So to find the time it takes for her to complete the bike throw, we use the power of a bench press and use that proportion for her weight, and it was approximately 230 watts. And the time was equal to the air resistance times velocity squared, where we used the air resistance of the bike itself, not including the rider, the length of the bike throw, divided by the power with which she throws the bike.
Results. Using our model, we calculated that if both bikers start at the same point, Winder's bike throw would have put her ahead by 1 2/100 of a second. Additionally, after Winder executes the bike throw, her bike would remain ahead of the other rider for approximately 1 2/100 of a second. At the calculated velocity, this allows the bike throw to be effective from 19.5 meters to 2 meters before the finish line. However, since it takes approximately 1/10 of a second for Winder to throw her bike, she needs to throw her bike before the last 2 meters of the race. The most effective point to throw her bike would be 2 meters before the finish line. Additionally, 0.6 of a meter can be made up with a perfectly executed bike throw if the other biker does not execute a bike throw, and the biker has the same parameters as Winder. The equation for the distance gained is equal to height times 1.023 over 2 times the sine of pi over 3, which comes from that the declination angle of Winder's arms is approximately 60 degrees, times the mass of Winder divided by the mass of the bike plus the mass of Winder. Limitations. The mechanical friction is just restricted to 0.5%. While most Olympic bikes have a mechanical friction of approximately 0.5%, we cannot guarantee that this is the same bike that Ruth Winder used. Additionally, we do not integrate the force of air resistance on the rider as the rider's position changed through the bike throw. We know that the position of the rider changes slightly during the bike throw, but we do not account for this. We also did not account for the rotational inertia of the wheels of the bike. We assume this to be negligible. According to our model, the road must be flat for our model to work. Our model also assumes that there's a proportional mass to arm power ratio for bench press. It also did not account for differences between men and women. Our model also assumes proportional arm length to height ratio is equal for every person. We also estimated that the front of the wheel makes up 5/12 of the area of the front of the bike. Our model does also not reflect the different positions in holding the bike. Ladies and gentlemen, this concludes our presentation. Thank you for watching our presentation. Have a nice rest of your day.